Okay, in the last lecture, you learned about the quark model, but how do we know that quarks have any reality? It was convenient to describe the quantum numbers of hadrons, but how do we know they are real? Well, it turns out that the Rutherford scattering formula for elastic scattering of point-like electrically charged particles like the proton or neutron is violated at high energy. And we sort of were led to this when we discussed the nucleus, that if you got to high enough energy, you could start to probe the charge distribution of the nucleus or the nucleon in general. And in doing so, effectively what we're learning is that the Coulomb scattering formula that becomes part of Rutherford scattering needs to have form factors introduced to describe the scattering cross-section, that is the probability to scatter. To account for that extended charge distribution. But more than that, if we go to even higher energies and hit it with some particle, let's say namely the electron, to use an electron as our probe, the proton and neutron actually break up. And this is known as deep inelastic scattering. Inelastic because the proton is no longer remaining intact. And it's this equation here, electrons say scattering off a proton leads to a scattered electron and then X, which can be a collection of particles coming out from that collision. And so that modifies Rutherford's scattering formula. And instead of form factors, we are going to have so-called structure functions. In this formula I'll show next, it'll be labeled F1 and F2 in the scattering cross-section. So we'll have a formula like this one here, which is this cross-section per unit so-called solid angle. But you could think of it as the rate of scatterings into specific angles when properly normalized. But the first part here, shown in the very first part of my expression, I've used the fine structure constant alpha squared instead of, in terms of the constituents of like electric charge and 4 pi epsilon naught. But that's Rutherford's scattering formula there. So that's Rutherford scattering, including the 1 over sine to the 4th. Right, remember that sharp dependence on scattering angle, 1 over sine to the 4th, theta over 2. But there's this extended part here where we've introduced these new functions, f1 and f2, and as angular pieces, cosine squared of theta over 2 and sine squared theta over 2. So it's definitely not behaving like point-like scattering between, say, an electron and a proton, leading to an electron-proton final state. Something else has happened and the formula's gotten more complex, okay? However, despite it becoming more complex, when analyzed, we can start to see that in fact it can be simplified again. In fact, we can find that point-like scattering is restored if we assume that the hadrons themselves are composed of point-like particles. So in other words, when we probe the proton with an electron and we have high enough energy, which by the way means small enough de Broglie wavelength, I can start to probe the structure inside the proton, and I could have a Rutherford scattering off of one of those charged constituents, the Coulomb scattering. Now, those constituents were dubbed partons by Richard Feynman. Parton meaning, it's part of this particle. And not being so bold yet to say those are the quarks. And we'll see a reason why we can't say that they're all just the quarks. So we call these partons. And since there's more than one of them in the proton, in particular for baryons, we assume there are 3. Each one carries some momentum fraction, let's call it x, of the momentum of the proton or neutron, whichever baryon we're talking about here. But x will be our label for the fraction of the momentum a parton carries within the proton. And what can happen now is that the incoming electron can undergo Rutherford scattering off of the electrically charged constituents, and then everything's restored from Rutherford scattering. All those same equations still apply. And I can show this kind of diagrammatically here. We have an electron coming in. It's going to scatter off a proton, but the proton can be thought of as those three quarks that comprise a baryon. And you're going to have a scattering off of one of those electrically charged quarks, knocking it out of the proton. And that's why the proton breaks up. You do have a remnant, and that's going to become a spray of particles, but the quark will come out that was knocked out. Of course, we can't actually measure directly that quark, and that's a whole different story about the strong force, the strong nuclear force. But nevertheless, the scattering form would behave as if you've scattered off of a point-like constituent inside the proton or neutron. Moreover, that scattering cross-section, that scattering rate, is more or less independent of the exchanged squared form momentum. So the electron will exchange some momentum to the proton, indicated here by the exchange of one of the force-carrying particles, like a photon. And the higher the momentum squared of that particle that's exchanged, you can think of it as having a smaller de Broglie wavelength. And the smaller the de Broglie wavelength, the smaller the feature size you can probe. But yet the scattering from the data appear to be more or less independent of that q squared, that form momentum squared. In other words, we're not seeing any structure of the partons themselves. They appear to be point-like. Okay, that's what it's telling us. So given that we have a new model now, that the hadron is comprised of partons, but they are point-like and electrically charged, we can rewrite those structure functions F1 and F2 in terms of those partons. Namely, if we assume that the partons are the quarks that we've talked about, those are the electrically charged ones, and I'm not going to motivate how this was calculated, but these structure functions that go into that previous equation on the last slide, F2, which in principle depends on the momentum fraction of the parton x and this q squared that's exchanged, but it can be written in terms of the squared electric charge of that quark times its momentum fraction, and then times a probability to find a quark of that type. Remember, type is called flavor. So a quark of that flavor at that momentum fraction. And you sum over all the flavors, that is types of quarks. Now, if your proton had only up and down quarks, that expression would look like this. You would have the charge squared. So up type quarks are 2/3 squared for the charge squared. Down type quarks are minus 1/3 squared. Multiplied by x, and then you have the probability to find an up-type quark or the probability to find a down-type quark. That's how the model goes, by expressing the structure function F2 in terms of those probabilities to find up or down quarks times their electric charge squared. So this is how we're going to recover Rutherford scattering. We're assuming they're point-like with those fractional charges I've discussed with you. Okay. All right. But what do we really find from these experiments? In reality, it turns out the proton is comprised not just of up and down quarks. And those up and down quarks do not necessarily have exactly 1/3 of the proton momentum, right? So baryon, we said, had 3 quarks. You might naively expect it's shared evenly across the 3 quarks, so being 1/3. In practice, there's a distribution of momentum fractions when you compile the data from many of these deep inelastic scattering experiments. So from those data on those scattering cross-sections, that is those scattering rates, and using those formulas I just presented to you, you can start to extract the probability densities for each of the types of quarks. And you get a diagram like this one here. So it's a distribution, it's not just a single value. So this is plotted as a function of x. That is the momentum fraction of the proton for one of these quarks, one of these partons. Now, you might think, well, it probably shouldn't be exactly 1/3 because it's a bound state. they're constantly in some sort of orbital motion. Sometimes it might be moving fast, sometimes slow. So it's going to be spread around maybe a third though. And we can see here from the blue and green distributions, they are a distribution. Note that the fraction x is on a log scale. Here's 1/10, 100th, and 1,000th. And what we call the up and down valence quarks, we'll call that UV and DV. These are the so-called valence quarks, which define the quantum numbers of the proton, right? When we made a proton as 2 up quarks and a down, if we infer those things out, we do get a distribution about a peak value. That peak value, though, looks to be a bit less than 0.2, maybe 0.15. So it is less than a third, which is a little strange, but it is spread around in value. But notice there's some other quarks in there. What are those? Turns out there is a so-called sea of other quarks and antiquarks inside the proton. So the quantum numbers were defined by the up and down valence quarks, but you can also have some sea of other quarks and antiquarks in the proton. The up and down define the quantum numbers, as I said. And by the way, notice that the area under the blue curve, the up-type curve, looks to be twice that of the area under the down-type valence quark, which makes sense. The proton was defined by quantum numbers as being 2 up quarks and a down quark, so the up-type valence quark should be twice as much probability that you hit one. But there are all these other quarks, but generally, if you add another quark, you've got to add an equal amount of antiquark because you want the sum of quantum numbers to be kind of neutral, give you no net charmness, no net strangeness to the proton, right? So that means our structure function, which I wrote in terms of up and down quarks, gets more complicated as shown here because we've got to add all the types of quarks there are. So along with the up type quark, I could have had anti-up, which also has a charge of -2/3, which squared gives me 4/9, or charm type quarks. Or the down type quark, I could have anti-down, I could have strange and anti-strange, and bottom and anti-bottom. And the proton has a little bit of all this. Those are the so-called C quarks. And you can see distributions, for example, in magenta, here is the charm quark density inside the proton. But the anti-charm is assumed to be equal to the charm density so that the net charm quantum number is 0. But let's come back to the point that the peak of the valence quark is not at 1/3 of the proton momentum here. Right? It was supposed to have that, but it is not having 1/3. And that's because the proton is also, the partons that make it up also contain gluons, the carrier of the strong nuclear force. That's how the quarks interact with each other when they're orbiting. They might exchange a gluon. But as they do so, the gluon's in motion and is carrying some of the momentum of the proton as well. And it turns out half of the momentum of the proton, on average, or roughly, I should say, is carried by these gluons. So I'd like to end this picture that although this quark model seemed very simple, and it does explain the quantum numbers of these particles, the actual dynamics inside a hadron, inside the proton, is quite complicated. You don't just have those 3 quarks. You've got this mass that's got quarks moving around, some popping out of a vacuum and then annihilating back into the vacuum. And it's just that the net quantum numbers are such that you have 2 up quarks and a down quark. Okay, so let's end this lecture on hadron structure there.